Hi, I'm Professor Goins. In this video, I want to look at the even and odd identities for the sine and the cosine function. Let's start by looking at the unit circle. If I look at an angle theta, then that's going to give me a point on the unit circle, say A comma B. And then if I look at the angle negative theta, so it's the same amount of rotation, I'm just going in the opposite direction. So I'm going in the clockwise direction as opposed to the counterclockwise direction. That would give me this point on the circle right here. Well, how is this point related to this point? We can see that the horizontal distance did not change, so therefore the x-coordinates match, but the y-coordinates would be a reflection in the x-axis, which means that this point here would have the same distance to the x-axis as this point does, but it's an opposite sign. So therefore, if this point is A comma B, then the point on the circle related to negative theta would be A comma negative B. All right, well, what does that say about the sine and the cosine? In particular, the cosine of the negative angle. So the cosine of this angle down here, of course, is the x-coordinate. And notice that this x-coordinate is the same thing for this angle. So that means that the cosine of negative theta is the x-coordinate on the circle, but that has the same x-coordinate as the cosine of theta. So therefore, the cosine of negative theta is equal to the cosine of theta. And what that tells me is that the cosine is an even function. Now let's look at the sine. Sine of negative theta, that's the y-coordinate corresponding to this point, which is negative b. So the sine of negative theta is negative b. On the other hand, b, so the positive b in this case, is the sine of theta. Therefore, the negative b value is negative sine of theta, and that gives me sine of negative theta is negative sine theta. Said differently, the sine function is odd. We have another way to see that sine and cosine are even and odd. And remember that the definition of even and odd had to do with the symmetry of the graph. If I look at the graph of the cosine function, it's symmetric with respect to the y-axis, meaning that if I look on either side of the y-axis, this side is a mirror image of this side. As far out as I want to go here, I can rotate it over 180 degrees and those sides will match. On the other hand, the sine function is symmetric with respect to the origin, meaning if I use the origin as a pivot point and I take, say, this first hill and I rotate it 180 degrees, this hill would match this valley. This valley would match this hill, so on and so forth. That means that it's an odd function. And there's two different ways to kind of interpret even and odd functions. We can either look at it graphically with the symmetry, or we can look at it algebraically with these properties of functions. Okay, let's use the even and odd identities for sine and cosine to evaluate a couple of trig values. Cosine of negative pi over 4. Well, if I use this identity right here, negative pi over 4, I can replace that with positive pi over 4, giving the cosine of negative pi over 4 would be cosine of positive pi over 4. That's one of our common angles in the first quadrant, which is root 2 over 2. On the other hand, if I look at the sine of negative pi over 4, this would be the same thing as negative sine positive pi over 4. Sine of pi over 4 is also root 2 over 2. In this case, then we get negative root 2 over 2. If I look at the unit circle, just to verify that, I know that pi over 4 is this right here. So in, of course, degrees, it's 45 degrees, so it splits the first quadrant in half. So this angle would be pi over 4. This angle right here would be negative pi over 4. And we see that, of course, the x-coordinates match. The x-coordinate for negative pi over 4, the x-coordinate for pi over 4 match exactly. They're both root 2 over 2. However, if I look at the sine of negative pi over 4, so if I rotate down here to negative pi over 4, we see that the y value is negative, and it's the same distance from the x-axis as this one here, which, of course, the y value here is root 2 over 2, so therefore this one is negative root 2 over 2. Let's look at another couple of examples. Okay, let's find the cosine of negative pi over 6 and the sine of negative pi over 6. Okay. The cosine of negative pi over 6 is the same thing as the cosine of positive pi over 6, which is root 3 over 2. On the other hand, the sine of negative pi over 6, negative sine pi over 6, which is negative 1/2. Okay, so what I can do is I can take a negative angle and I can turn it into a positive angle if it's the cosine, I just ignore the negative. If it's the sine function, I take that negative and I pull it out front. Okay. Now, remember that the remaining trig functions, the tangent, cotangent, secant, cosecant, they're all built as ratios of sines and cosines. So what I can do is I can use this relationship right here, that the cosine is even and the sine is odd, to determine whether or not the remaining trig functions are even or odd. Okay, let's take a look at a couple of these. If I look at the function, let's look at the cosecant of negative x. Let's see what that simplifies to. Well, remember that cosecant is the reciprocal of the sine function, so this would give me 1 over sine of negative x. Since sine is an odd function, this negative can be brought out front. Then I would have the negative reciprocal of the sine function, which is the negative cosecant function. And what that tells me is that the cosecant function is odd, because if I have a negative on the inside, that's equivalent to having the argument have the opposite sign and then the function itself have a negative in front. So I can just take this negative and put it out front. That means it is an odd function, and therefore I know that the graph is symmetric with respect to the origin. Now we can check that by looking at the graph of the cosecant. If you watch one of our other videos, we went into detail of how you can generate the graph of the cosecant. I'll reproduce it here fairly quickly, but again, just to verify that it has that symmetry. Okay, let's start with the graph of the sine function. And remember, in order to graph the cosecant function, it's undefined at the zeros. And then if I take the reciprocal at each one of the maximums or minimums, the values match. And then we have this sort of like a contained parabola sort of a shape. And again, I explained why in the other video, but it looks like this. And it's bound between these vertical asymptotes. Okay, so just really quickly, this blue graph then would be the graph of the cosecant, and we can see that it's symmetric with respect to the origin. If I take this sort of parabola-ish shape, then if I rotate 180 degrees, this one that opens upwards would match this one that opens downwards. Same thing as I expand to the left and to the right. Okay. Another common graph is the tangent, so let's take a look at the the tangent function. Let's see if we can determine if that's even or odd. And then let's look at the graph to verify. Okay, so again, tangent, the way we're going to check to see if this is even or odd is we're going to use the algebraic property, and then we can verify it with the graph. But let's see, if I take a negative on the inside of a tangent, tangent being sine over cosine, this would be the sine of negative x over cosine of negative x. Sine is odd, therefore I can pull a negative out front. Cosine is even, therefore I can ignore the negative. And then I've got a negative sine over cosine, which is negative tangent, telling me that it is an odd function. Let's verify with the graph. Again, the graph of the tangent is a standard curve that you will see. Let's take a look at what it looks like. Remember that there are vertical asymptotes here, which would occur when the denominator is 0, meaning at odd multiples of pi over 2. So this would be 1 pi over 2, this would be negative pi over 2. I'd have another one at 3 pi over 2. What happens is this pattern just repeats as I go out to the left and to the right. Okay. And if I just look at this middle one here, I can see again if I use the origin as a pivot point, this part of the graph in between these first two asymptotes rotate 180 degrees and match this one exactly. Same thing as I go farther and farther out, this would end up matching this exactly. So we can see visually that it is an odd function. And you can check for the remaining trig functions as well. I'll let you can do that on your own. If you have any questions on it, feel free to leave it in the comments. But it's straightforward, just like we did with this one and this one.